In our first section, we introduced the idea of a limit, and we weren't very precise about it. And we talked about what happens when we get close to some value. And we're going to continue using that definition here, but we're going to introduce a little bit more notation in this section and do some more computational examples and actually see where some of the computational examples break down and why we're going to need to develop some better techniques for calculating these things. Our definition then will be, suppose that f of x is a function where it's defined near the number a. Then we write this limit as x approaches a, and we say it equals L if we can make the values of f of x arbitrarily close to L by taking x close to but not equal to a. So again, we're looking at the behavior of the function as we get near this value a. We don't necessarily care about what happens at a. The function might not even be defined there. But we want to know about the behavior of the function near that value. So if we go ahead and look at an example here, we want to guess the value of the limit as x approaches 1 of x minus 1 divided by x cubed minus 1. And again, when we talk about what happens when we're close to it, that's all we can really consider, because if we plugged in 1 here, we'd get 1 minus 1 over 1 cubed minus 1. So we get 0 over 0, and that's not defined. Remember, we can't divide by 0. So we need to use some sort of numerical tool to figure out what's happening here, at least for the moment, before we learn some more techniques here and rules. So we want to make a table of values for values close to 1. So this is similar to what we did in the last section. I'll go ahead and make my table of values here. And so on the one side here, I've got what happens as we are slightly less than 1. So 0.5, 0.9, 0.99, and 0.999. And we see that we are sort of zeroing in on 0.33, seems to be a common value here. And on the other side, if we start above 1 and sort of go from there, again, 1.5, 1.0, well, one of these is a typo, so let's just get rid of it. And again, we see we're coming close to this 0.33 here. So 0.33 is really close to 1/3. So we would make the guess then that it seems like this limit is going to be 1/3. Now let's go ahead and look at a graph and see what's happening here. So I just pulled something up on Desmos. So when we're looking at the limit as we approach 1 here, and if you notice, again, if I just click on 1 here, that point, if I can get it highlighted, we see that 1 is undefined. But we're not concerned so much as what the value is at the point. We just care about the behavior near the point. And we can see that near the point, we are really close to this 0.33. We're really close to 1/3. So this seems like a reasonable guess for us to make, at least based on our numerical evidence. Now, for another example, let's look at this. So the limit as x approaches 0 of sine of x over x. Now, again, if I just plug this in, I get 0 over 0. So I get something that's undefined. So this numerical approximation is at least a good way to start. So maybe you want to hit pause here and try doing this on your own here and come up with values near 0 to plug in and see what's happening here. And if we go ahead with the sort of progression that we were doing last time in these last few examples, and we are trying to approach 0 from values a little above and values a little below. If we use 0.5, we get 0.959. If we use negative 0.5, we also get 9.59. If we use 0.1, we get 0.998, and the same thing with negative 0.1. And if we go out to even closer to 0.01, we actually get quite a few values. And I realize I went out more decimal places here, but just to illustrate how close we're getting here. So it really seems to me that this behavior is that this limit is getting really close to 1 here. And again, let's consult the graph and see what's happening here. So if we look at the graph of this function and we're looking for the behavior near 0, again, at 0, we are undefined. But if we use a tool like Desmos here, it actually says that near this point where it's actually equal to 1, because it is rounding to such a place at so many decimal places that it's just going to get rounded up to 1, and it really can't distinguish the difference. So this really seems like a reasonable guess for what our limit is going to be here. However, we do have to be careful when we're computing limits numerically, and we're going to have to come up with some better, more sophisticated methods for dealing with this. And one of the reasons we can see that is in this following example. If we want to find the limit as x approaches 0 of sine of pi over x. And if we wanted to do this same sort of analysis that we did before, and maybe you want to hit pause here and try to compute this on your own. If we do the same analysis and I start with 0.5 or 1/2, then what I'm going to get is sine of pi over 1/2. And if you remember how fractions are going to work here, so this is going to equal the same thing as sine of 2 pi. And so we just get 0 here because sine of 2 pi is 0. So if you remember your unit circle, remember that when we're dealing with sine functions, we're looking for the y value. And if we're looking at these radian measures, that 2 pi would be going around the circle 1 complete time and ending on this x-axis. And at that point, the y value is 0. So we get sine of 2 pi is 0. And if we went to 1/10, 0.1, we would get sine of 10 pi. And again, if this is going to equal 0, it would be the same sort of thing as going around the unit circle 5 complete times and then asking what the y value is at that point. Well, we're still at that same point there. And as we keep going, 0.01, that's the same thing as 1/100th. So we get sine of 100 pi. And again, this is going to be equal to 0. And we would guess, based on this information, as we did before, that this is going to equal 0. However, if we look at the graph the way we have in the previous two examples, we'll see something different. And we see that something that you probably haven't seen too often before as far as a graph goes is that you get this very fast oscillation happening in the middle here. And that's just the sine curve bouncing up and down faster and faster between that. And the thing is that for any of the values here, any sort of integer value, we're going to get 0 when we do that. So we are just happening to pick points along here that are 0, but we could have just as easily picked points that were always going to be 1 as we get closer here. So we run into an issue here, and in this case, what we would say is that this limit does not exist. Because if we go back to this definition, I cannot make the value arbitrarily close to some value by picking x close enough to a. Because if we're looking at these oscillations that are happening here, there is no value where we get close enough to 0 where everything has to be super close to that value. We're always going to be something between -1 and 1, and that's not precise enough to be considered a limit.